Welcome back to Introduction to Statistics and more discussion of estimating a population mean. Before we get into the calculations necessary to estimate a population mean, let me give you another way of looking at this. So let's take a look at this diagram. This is a little bit of information about the distribution of the random variable x. I've given you the mean. However, when you are working with this stuff, you don't have the population mean. You know it's out there somewhere. That if you could survey the entire population of interest, you could calculate that mean. You don't know what it is. What you do know, or what you will know as soon as I show you how to calculate it, is your sample mean and your margin of error for the sample you have just taken. And you will be able to say, yes, I am 95% confident that the mean of the population is actually within my margin of error. And if you take another sample, it may just fall that way. You would still be saying that you're 95% confident that the mean of the population falls within your margin of error. If you keep sampling using exactly the same techniques of sampling and analyzing the data and performing these calculations, you may get those two samples and those two means and margins of error on different trials and different samplings. One of them, as you can see, actually hits the population mean again. The population mean is within the margin of error stated. But the fourth time, perhaps, that you sampled, maybe you actually missed it. You won't know because you don't know what the population mean is. But that's why you're not 100% confident that what you're doing is stating the actual mean. And it's why you have that margin of error built into it, because you're not sampling the whole population. You are basing your inference of the population mean upon your sample. So if you continue this process using your methods and calculations, it looks like, yes, you should be pretty confident that the mean of the population is within your margin of error. But wow, those margins of error look kind of big. Is there some way we could decrease the margin of error? Well, yes, there is. Let's do that graphically first. This is the same mean, the same distribution, the same sample means within. Each of these is the same as it was before. However, the margin of error has shrunk. And now when you look at it, you can see multiple times when it actually misses the mean. So if we decrease the margin of error, we cannot be as confident that we are actually going to capture, in a way, the mean within our margin of error. So that is the trade-off. If you want to be very, very confident that you have captured the mean within your margin of error, then you have to have a large margin of error. If you are okay with less confidence that you have captured the mean, then you can have a smaller margin of error. I refer you to your book for most of the properties of the t-distribution, or you can look it up online if you prefer. But the most important one that will affect the way you use the t-distribution is that the t-distribution is different. Okay, it's not always the same. It's different for different degrees of freedom. Different degrees of freedom. Now that's a term we have mentioned before, but it's going to become even more important now because in the calculation we used it in previously, we calculated it a few times and then turned to our calculator and let it do it for us. Well, Mr. Gossett has developed the t-tables for you, but you still need to use degrees of freedom in order to interpret what's in the tables. What is a degree of freedom? The degree of freedom, or DF, for any sample is equal to the number of individuals in the sample minus 1. That's it. I discussed some rationales for that earlier in the class. I'm not going to go into it right now. So here's a picture of a t-distribution. Looks a lot like a normal curve, doesn't it? And you'll see that if you go to your book and look at the list of properties, that they are similar but not the same. All right, so there's the formula for n minus 1 degrees of freedom. But for now, you will instead refer to the chart, which is why you need to know the degrees of freedom. Another important thing to note about the t-distribution, especially about the t-table itself, is that it's kind of set up backwards from your z-table, backwards in different ways. For instance, the t-table deals with the area to the right of whatever value you have of interest. And we would call that the t area, t sub area, just to denote what that means. Okay, so let's say the area here equals 0.10. That means we can change t sub area down here, get it erased, to t sub 0.10. That's the area for which we want to find the t value. To do this, we not only need to know in what area we are interested, we also need to know how big our sample is. So let's say, okay, this is for small samples. Above 30 works best, but you can still use it to get an approximation for something as small as 20. So let's do it for 20. Push all this aside for the moment. All right, here is a t-distribution table. It is not the t-distribution table from your book. It's not the t-table from your book. This says tail probability goes across the top. It's the same thing as you have in your book, only your book identifies those values as the area in the right tail. So that is reminding you that the t-table is everything to the right of the value of interest. All right, so we were working with an area of 0.10, so we will go down that column. We were working with a sample size of 20, that means the degrees of freedom is one less than that, or 19, and there is the value. So we go down from 0.10 and across from 19, and we arrive at the value 1.328. Ta-da! We have found our t-value. All right, let's move this out of the way and pull back what we had been working with. And we did discover that t sub 0.10 equals 1.328. So what does that mean? Well, if you look at this t-distribution where the mean, the sample mean is there, above it you have 1, 2, 3 standard errors of the mean, and below it you have -1, -2, and -3 standard errors of the mean. So 1.3 standard errors would be right there. Well, whoop-de-doo. What does all that mean? Well, the interesting thing about confidence intervals is you get to decide how confident you want to be. Now, if I'm having eye surgery and somebody's going to install a shunt in my eye to relieve pressure, I want them to be pretty confident that they know the dimensions of that shunt. And I want the manufacturer of that shunt to be pretty confident that they have manufactured that to very exacting specifications. And it's not too big and it's not too little, so it works just right. I'm probably going to want about 95% confidence in what they're doing. 95% confidence that the sample that they took to test how good their equipment is has truly captured the mean of the population. So let's talk about a margin of error, and we will get to how the confidence level influences the margin of error. So the margin of error is represented by a capital E. Yes, we used it for probability, but here we are using it for margin of error. And it is equal to the t-value times the standard error of the mean. Or you could write that as the t-value times the formula for the standard error of the mean. So this will be the number that you add and subtract from the mean that you calculate to say, here is my margin of error. I think the mean is between these two numbers. So now you see why we needed to know how to find a t-value. So let's look at an example of exactly how we find a confidence interval. So here's the first example. A simple random sample of size n equals 20 is drawn from a population that is normally distributed with a sample mean of 50 and a sample standard deviation equal to 8. We are asked to construct a 98% confidence interval for mu, for the mean of the population, because that is always our goal. Take our sample and say something about the population. We will deal with the confidence interval first. Before we do that, I need to mention one thing. Earlier I said we can do these calculations for sample sizes less than 30, and that is true. However, if we are going to do it with a sample size less than 30, it must be from a population that is normally distributed. If the population is not normally distributed, then we can't do it. And of course you don't know exactly that, but if everything indicates the population is normally distributed, then you can be pretty safe using the t-table. In other words, if you're talking about baby's lengths or the weight of a certain make of car, okay, you would expect those to be normally distributed. So you could take a sample size of 20 and apply these techniques. For something like students who have sat through Professor Rose's stats class and are taking a national stats test, you would expect the results to be skewed left, so you couldn't take a small sample size. You must not forget the empirical rule. We're looking at a 98% confidence interval. Let's express that as a decimal. 98% of the data, 98% of this distribution would be approximately between here and here. Okay, it's not out to 3 standard errors of the mean, but getting close. Please remember that your t-table only gives you the area under the curve to the right of the value of interest. So it's only going to give you this area here where the arrow is. And notice the 98% that we're looking for confidence with is right there in between the two. So what we need to know is what is the area on either side of that 98%. And how do we get that? Well, if we subtract that 98% from 1, we get 0.02. But half of that is located here, and the other half is located here. But we don't know that value yet. That's why we need the t-table. Now it is time for me to introduce you to a Greek letter, the letter alpha. And alpha is the value that you get when you subtract your confidence from 1, and this value is the area on either side of that 98% confidence. If alpha is 1 minus 0.98, each of these areas are alpha divided by 2, half of alpha. And that area is 0.01 in each case. Little tiny bit of area on either side there. We're going to look up this one in the t-table. And here it is. All right, we are looking up the value 0.01 of this distribution. So let's see, 0.01 here. We will be going down this column. But where do we go across? Well, we have the value n equals 20, which would be right there. However, what we need is degrees of freedom, which is 1 less than that, or 19. So we're going to be going across this row, and we went down this column. So there is our value, 2.539. Let's return to the previous page, and let's record that t equals 2.539 from the table. Now, my time is about to expire for this video, so I will upload it, and we will continue this exercise in the next video.